Hello everyone, today I'm going to take you through the May-June 2023 paper and I'm going to give you as much detailed explanations as possible. Let's get to the work. The first question says, which vector diagram correctly shows the force Z as the result of forces X and Y? In this diagram, we are trying to test your understanding of the head-to-tail method. The head-to-tail method is used when showing the resultant vector. So, if we have x and y as the component vectors, they must be aligned in such a way that the head of x and the tail of y, they join each other. If we look here in A, we can see that the tail of x and the tail of y, they are joined here. And this is not correct. We want the head and the tail. That is the same case here. We have the tail of y and the tail of x. Let's look at C. We have the head of x and the tail of y, and this is what we are looking for. However, the resultant vector z should point from the tail to the head of our vectors. So here we can see it's pointing from the head of this to the tail of this, and we cannot take that. Let's look at D. Obviously, D will be the correct answer after elimination, but let's just prove it is. We have X and Y, they are showing head of X and tail of Y. Then we have the resultant Z from the tail of X to the head of Y. This is the correct answer. Number 2 says, an object falls towards the surface of the earth. The object is falling at its terminal velocity. Terminal velocity is a constant velocity. Which statement is correct? All right. One thing we know about terminal velocity is that when an object reaches terminal velocity on its fall, let's say it's falling in this direction, that means the resistive forces and the forces which are responsible for acceleration, they are balanced. So the resistive forces are usually the air resistance for an object that will be falling, and the forces responsible for acceleration, in most objects, that would be the weight of the object. Now, when the upward forces and the downward forces balance, it means there is no more resultant force. And when there is no resultant force, there can be no acceleration. This is the case we have here. Now let's look at the options given. There is air resistance, of course there is, and the acceleration of the object is negative. Well, we said no acceleration, so it's not correct. There is air resistance, and the acceleration of the object is 0. B is the correct answer. We do have air resistance, which has managed to balance out with weight. When the two balance, there is no acceleration. So that's why B is correct. Let's eliminate C and D just for fun. C says there is no air resistance. Well, we know that if you have an object and it is falling down, the weight of the object will definitely be there. So if there is no air resistance, then this object is always going to accelerate because it is always going to have the resultant force. So C is wrong because of that. There is no there is no air resistance. Again, for the same reason, there definitely is air resistance. Number 3 says the graph represents the motion of a vehicle. What is the distance traveled by the vehicle in 400 seconds? Now, some important things to take note of here is when we have a speed time graph, the area under the graph represents the distance traveled by the object. So our task here is to find the area under the graph. Okay. Something to also take note of, although not relevant for this question, is that the gradient of the speed time graph has a meaning, and gradient is equal to acceleration. Okay, now back to area of this graph. Area is equal to, this is a triangle, so 1/2 times base times height, the popular half base times height equation. We have 1/2, the base is 400, the height is 20. This gives us 4,000. So the distance traveled is 4,000 meters. Number 4 says, on the earth a spring stretches by 5 centimeters when a mass of 3 kg is suspended from one end. The gravitational field strength on the moon is 1/6 of that on earth. Which mass on the moon would stretch the spring by the same extension? Now our setup is going to look something like this. Alright, so the spring extends here, and it extends because of the weight. And in this case, our weight is 30 newtons. We get it from saying weight equal to mass times gravitational field strength, which we know on Earth is 10. Alright, so if you go to the moon and you provide a weight of 30 newtons, you will be able to extend this string by 5 centimeters. In other words, the question is saying which one amongst these masses will give you a weight of 30 newtons when you are on the moon. Now that's an easy question. We are going to say, okay, weight is equal to mg, as already mentioned. The weight we want when we get to the moon is our good old 30 newtons. The mass which can give us the 30 newtons is the one which we do not know. So we'll say M. Then the gravitational field strength when we go to the moon is 1/6 of the gravitational field strength on Earth, which is 10. Solve this equation, you have the mass you are looking for. So if you make M the subject of the formula, you will end up with 30 times 6 divided by 10, which gives us 18. So the answer here is 18. Number 5. A shopkeeper pours rice into a dish that hangs from a spring balance. He records the reading. A customer buys some pasta. The shopkeeper notices that the reading on the spring balance with just pasta in the dish is the same as it was with just rice in the dish. Which quantity must be the same for the rice and for the pasta? Let's get back to the diagram and see. Now our spring balance, it helps us to compare masses and subsequently weights. So if the spring balance is giving you the same reading, it means the mass of the objects you are dealing with is the same, or the weight of the objects you are dealing with is the same. So our answer is either mass or weight. Let's just pick one of those two from the options. We are given weight here, so our answer would be D. The spring balance does not compare densities, temperature, or volume. Number 6, a student determines the density of an irregularly shaped stone. The stone is slowly lowered into a measuring cylinder partly filled with water. Which other apparatus does the student need to calculate the density of the irregularly shaped stone? Okay, let us look at the diagram and see what we have. This setup we are looking at will help us to determine the volume of the irregularly shaped stone. Now, on top of volume, we are going to need the mass of the stone. Because the formula for the formula for density is density equal to mass over volume. So we have volume of the stone, now we need the mass. And what instrument do we use to measure mass of this stone? We need a balance. Number 7, a train is traveling horizontally in a straight line. A book is on a table in the train. The diagram shows all the forces acting on the book. How is the train moving? Now, this question is testing your understanding of the nature of friction. And friction opposes motion. This means if the book tries to go in this direction, friction will go in this direction. And with our diagram here showing that friction is going to be right, it means the book is trying to go to the left. That is what it means. Now, let us look at the options given and see which option makes more sense. It says accelerating left of the diagram. So, if the train tries to accelerate in this direction, then the book is going to have some inertia, and that inertia is going to make the book try to go in this direction. Now, as we see, we want the book to go to the left so that friction can point in the direction given in the diagram. So A is wrong. B, accelerating to the right of the diagram. The train is accelerating in this direction, and the book is going to want to go in this direction. Let me give you an everyday example. This is the seat of a car. Okay, and this is you sitting on the seat of the car. When the car accelerates in this direction, your head is going to swing in the opposite direction. Your head wants to go in the direction opposite to the acceleration of the car. This is the same situation we have. The train is accelerating in the right, and your book over there is trying to go to the left. Then friction says to the book, you are not going to the left. This is the friction we have. So when friction points to the right, it means the book was trying to go to the left. B is correct. I want to talk about C and D. When the train is traveling at uniform speed, that means it's not accelerating or decelerating. then the book is not going to experience any friction to the right or to the left. If the speed is uniform, it means no acceleration. And therefore, the book is not going to move to the left or to the right. The diagrams show 4 beams, each of negligible weight and freely pivoted. Which beam is not in equilibrium? When a beam is not in equilibrium, it means, first condition, there is resultant force. Second condition, it means there is resultant moment. We cannot talk about resultant force in these diagrams because we are only given the forces which are going downwards. We are not told of the forces pointing upwards. In other words, the forces at the pivot. So we don't have a way of using resultant force. We are going to check which beam is not in equilibrium by looking at the beam that has resultant moment. Now, we know there is a resultant moment when clockwise moments are not equal to anti-clockwise moments. So let's check the clockwise moments here. A, the clockwise moments will be due to the 6 Newton force, and we have 6 Newton meter. And the anti-clockwise moments will be due to the 3 Newton force, and they will be equal to 3 times 2, that is 6 Newton meters again. A is in equilibrium. Let's go to B. The clockwise moments are due to this 6 Newton force, and they are 12 Newton meters. That is 6 multiplied by 2. The anti-clockwise moments are due to this 6 Newton force, and they are equal to 12 Newton meters. In other words, 6 multiplied by that 2. B is in equilibrium. Then we go to C. The anti-clockwise moments are due to this 3 Newton force, and they add up to 3 by 1, that's 3 Newton meters. And the clockwise moments, they are equal to 6 Newton meters, that is 3 multiplied by 2. Now, C is not in equilibrium because the clockwise moments are not matching the anti-clockwise moments. We have our answer. Go ahead and show that D is in equilibrium. Number 9. An object of mass 1.2 kg is moving with a velocity of 2 meters per second when it is acted on by a force of 4 newtons. The velocity of the object increases to 5 meters per second in the same direction. For which period of time does the force act on the object? We know that F is equal to mass multiplied by acceleration. The force which is responsible for the acceleration in this case is 4 newtons. So we have 4 equal to the mass of the object is 1.2, and the acceleration is equal to V minus U divided by T. This is final velocity minus initial velocity divided by time. This is the formula for acceleration. You may have been given this formula as delta V divided by T. That is the same thing. So now we have 4 equal to 1.2 bracket, final velocity is 5, initial velocity is 2, then the time is what we are looking for. If we solve this equation, let's do that together. Okay, that gives us t equal to 0.9 seconds. So our answer is A. Our answer is A. Number 10. Which row about the change of energy in the energy store must be correct? Okay, A. Water pumped up to a high altitude dam. What's happening is gravitational potential energy. Yes, water gets gravitational potential energy and energy increases. That is correct. When you pump water up in high altitude, this water didn't have GPE, gravitational potential energy, but the moment it gets up here, it has gained that GPE. That GPE was provided by the pump. So A is correct. Let's eliminate B, C, and D. Water pumped up to a high altitude dam. The energy stored given is kinetic energy, which is not correct. Yes, the water is going to gain some kinetic energy as it travels up to the high altitude, but when it reaches that high altitude, the energy is going to be stored as gravitational potential energy. So the energy store is not Ke, B is up. We go to C. Air passes through a wind turbine. When air passes through the wind turbine, it is going to make the wind turbine to move. And we are going to see a transformation of energy from kinetic energy of the air to kinetic energy of the turbine, which can then be stored as electricity or some other form. So the turbine is definitely not getting gravitational potential energy. Neither is the air getting GPE. Again, air passes through a wind turbine. We are looking at kinetic energy of the air becoming kinetic energy of the wind turbine. But the wind turbine is not a storage. A woman of mass 50 kg has 81 joules of kinetic energy. What is her speed? We are going to say kinetic energy is equal to 1 over 2 mv squared. So if we substitute the data that we have, we can find V of the woman. So 81 is equal to 1 over 2 times 50 times V squared. That gives us V squared is equal to 2 times 81 divided by 50. But we don't want V squared, we want V. So V is equal to square root of 2 times 81 over 50. You punch that in the calculator, you are going to get C, which is 1.8. Okay. Number 12 says, a child runs up a set of stairs 4 times. The time taken for each run is recorded. Which time is measured when the child's use for power is greatest? Okay. Now we know that for the child to run up and down the stairs 4 times, this child is going to need the same energy. Same energy is going to be expended when they run up and down the stairs. So the formula for power is equal to work done, which is the same as energy, divided by time. If you look at this, work done is not going to change. Every time the child runs up and down 4 times, the work done is not going to change. What can only change here for us to calculate power is the time. Now, if the denominator is small, it means the overall answer is going to be big. Let me show you an example. 10 divided by 5 gives you 2. 10 divided by 1 gives you 10. So when the denominator is small, you get a bigger answer. And in this case, our answer will be power. So A is the correct answer. When you do work in a short amount of time, then it means you are working at a greater power. If you take too long to do some work, it means you were operating at lower power. That is the reason for A being correct. Number 18, a dam holds water in a reservoir. The height of the water in the reservoir is 15 meters. The density of water is given. What is the pressure due to water at the bottom of the dam? We say pressure is equal to height multiplied by gravitational field strength of the earth multiplied by the density of the water. So substituting the numbers, H is 15, D is 10, and rho is 1000. That gives us 150,000. So our answer is 150 kilopascals, or 150,000 pascals. A student uses a microscope to observe pollen moving on the surface of water. Which statement describes the reason for this movement? Water molecules are moved by microscopic pollen particles. Okay, before we answer this question, we are talking about Brownian motion. Now, with Brownian motion, we observe visible particles making zigzag motion. And it might give you a conclusion that this visible particle is lifelike. It has life, it is moving. But the truth cannot be further away. What is actually happening is this pollen particle is being bombarded by water molecules, which we are not seeing. They are microscopic. We cannot see the water molecules even using some of our lab microscopes. So the water molecules, they hit the pollen grain and the pollen grain moves. Then the other water molecules, they hit the pollen grain from this side, and we see the pollen grain changing direction. And it continues to happen over and over as long the water molecules have energy. So our answer here is going to be explaining the bombardment of pollen particles by water molecules. So A says water molecules are moved by microscopic pollen particles. Now, what is really more microscopic is the water molecules, not the pollen particles. So A is not correct. Water molecules are moved by pollen molecules. It's actually the other way around. Microscopic pollen particles are moved by water molecules. Okay, this is true. The pollen particles are being moved by water molecules. Pollen molecules are being moved by water molecules. Well, these are not molecules. For pollen, these are not molecules. These are particles. I think that is also true for here. Pollen, we are not talking of pollen molecules. We are talking of pollen particles. So our answer is C. Which statements about the evaporation of water are correct? Evaporation causes the remaining liquid to cool. That is true. Let me show you why. We have particles which have a lot of heat energy, and we have particles which don't have a lot of heat energy. So what is going to happen is, if the particles with more heat energy escape, or if they move away, then the particles with less heat energy are going to remain, and that means the remaining particles will be colder. So number 1 is correct. Number 2, during evaporation, the more energetic particles escape from the surface of the liquid. Again, that is true. The particles which have more heat energy, the particles which are at higher temperatures, they are more energetic than the particles which have less heat energy. So the energetic particles, they can break free from the liquid. Number 2 is correct. Number 3, evaporation only happens at 100 degrees Celsius. That is not true. We would rather say when we are at standard conditions, boiling happens at 100 degrees Celsius. By standard conditions, we are looking at standard pressure. So evaporation can happen at any temperature. Our answer would be option item 1 and item 2 only. That is option B. Number 16. Some hot water is sealed inside a metal can. The can is in a vacuum in outer space. The hot water slowly cools down. How does the thermal energy escape into space? Okay, so if this is our can, the water inside needs to, the heat energy of the water needs to pass through the wall of the can. that is going to require conduction. Then, once the water is outside of the pane, it needs to move through space. The only method by which heat can move through a vacuum is radiation. So our answer should be conduction followed by radiation. That is B. Number 17. The diagrams show graphs of displacement against time for 4 waves. All the graphs are drawn to the same scale. Which wave has the greatest amplitude and the highest frequency? Amplitude, we are looking at distance from the resting position to maximum displacement. So this is the amplitude here. And it's quite huge. The amplitude of A and the amplitude of B, they are actually equal. There are 2 units. That is the 2 units there. So when it comes to amplitude, A and B are the same. And they are also carrying amplitude which is bigger than that of C and D. So C and D have already lost because they do not have the greatest amplitude. Let's now consider the frequency. Frequency is defined as the number of oscillations per unit time. So, if we look at A and B, we can clearly see that A is doing more oscillations per given time compared to B. A is completing more oscillations per unit time. For example, 1 unit time, A has completed half an oscillation and B has completed less than a quarter of an oscillation. So A is our answer. Number 18. The diagram shows a ray of light entering a glass block. Which calculation gives the refractive index of the glass? Now we know that refractive index given by N is equal to sine I divided by sine R, where I is the angle of incidence and R is the angle of refraction. So if we substitute, we get, okay, before we do the substitution, let's sort out something very important here. The angle of incidence is measured between the ray and the normal. So the 50 given here is actually not the angle of incidence. It is this angle not given here. And that angle, we get it by saying, well, the normal and the glass are at 90 degrees. So 90 minus the 50, we get 40 degrees. So now when we go and say sine I, it is sine 40 degrees divided by sine 25 degrees. Here the sine 25 is clearly given, and it's the angle between the normal and the ray. Okay, so our answer is A. An object O is placed at point P near to a thin converging lens. The diagram shows 3 rays from the top of O passing through the lens. Each point F is one focal length from the center of the lens. Each point 2F is two focal lengths from the center of the lens. The object O is moved to point Q on the diagram. Which type of image is produced when the object is at point Q? I'm going to quickly draw the ray trace diagrams of the rays when our object is at point Q. Okay, so this is the ray trace diagram which I have drawn. Well, you may have memorized the appearance of the image when certain conditions are given to you, and that will be fine, and you'll be okay to use the memorized positions and nature of image. But in cases where you don't have the memorized version of the nature of the image, you can draw your ray trace diagram. And let me point out the important features of this ray trace diagram. There are straight lines, one which is starting at the head of our object. It passes through the optical center. This is our optical center of the lens. So this is the first straight line, which is blue, that I drew. Then the second line, which is this line, and it extends to that side. This line starts at the tip of the object, it gets to the focal, the converging lens, and it has to bend, and as it bends, it passes through the focal length. Now, if you continue or extend this line, it's going to meet the blue line. And where these two lines meet, that is the position of the image. So this is the image. We can clearly see the image is inverted and it is bigger. So our answer is B. Number 20. Which diagram shows the dispersion of white light by a glass prism? Dispersion of white light is basically the separation of different wavelengths of light when the white light moves from material of one optical density to material of another optical density. So white light is typically separated into red, orange, yellow, green, blue, indigo, and violet wavelengths or colors. Now we can see here we are moving from this medium X to the glass. At this boundary, we are moving from one optical density to another optical density. There must be separation of the colors. So there must be separation of colors, and that separation must happen in such a way that the light will be bending towards the normal, or all the light must be bending away from the normal. Okay, so A is out because there is no separating of light happening there. Okay, we look at B. B is showing the separation of light at this boundary. We are at the boundary, And we can see the red light is bending towards the normal, the violet light is bending towards the normal. So both wavelengths are doing the same thing, which is a good thing. And we go to this boundary. We are now moving from glass to medium X. At that boundaries, we want to see light moving towards the normal or away from the normal. So both rays must do the same thing. If we put our normal, we can see that light is moving, red light is moving away, violet light is moving away. Which is a good thing again, because the two rays are moving away in the same direction. So B is looking very good right there. Let's see D. What is happening to D? We can clearly see there is separation of colors there, red and violet, which is a good thing. But if we come here, red light is moving away, and let's see blue light. Blue light is moving towards the normal, and that is not good. C is out, because when red light moves away from the normal, violet must also move away. It should not move towards the normal. C is out. Then D, without wasting much time, there is clearly no moving away or towards the normal which is happening with the violet light. Yet it must be refracted when it moves from glass to medium X. So the fact that violet light is not refracting shows we have a problem. Number 21. Visible light has wavelengths in the range 4 times 10 to the minus 7 meters to 7 times 10 to the minus 7 meters. What is the range of frequencies of visible light? Okay, we can use the good equation V is equal to F lambda, and F is therefore equal to V over lambda. Now, what is left for us is to substitute. When the wavelength is 4 times 10 to the minus 7, what is F? 3 times 10 to the power 8, which is the speed of all electromagnetic waves, including visible light, divided by the wavelength, which is 4 times 10 to the minus 7. This is going to give us, we get this frequency. We also do the same for this other wavelength. F is equal to divided by so these are the frequencies which correspond with the given wavelengths. We look at our answers, we find that D is the one which has ranges. Student X fires a starting pistol which produces smoke and sound. Student Y is standing 100 meters away and sees the smoke the instant it is produced. The speed of sound in A is 340 meters per second. What is the time delay between student Y seeing the smoke and hearing the sound? So, the pistol is going to be fired at the starting line, and the sound is going to travel 100 meters to student Y. This is 100 meters. The time for sound to travel the given distance is what we are looking for. We are going to say time is going to be distance over speed, and that is 100 divided by the speed given here, which is 340. We punch in our calculators, we will get our answer would be A. Number 23. An unmagnetized piece of soft iron is placed close to a strong permanent magnet as shown. What is the induced polarity of end X of the soft iron, and in which direction does the magnetic force act on the soft iron? When you put a magnetic material next to a permanent magnet, these two, actually the soft ion is going to be attracted to the permanent magnet. This end of the soft ion must be a south pole in order for it to be attracted. It has been induced to be the south pole. So we are looking at C and D. Now, when it becomes a south pole, it goes towards the permanent magnet. So to the left, which gives us C. Number 24. A plastic rod is rubbed with a cloth. The rod and the cloth both become charged as electrons move between them. The rod becomes negatively charged, so it gains electrons. Which diagram shows how the rod becomes negatively charged and shows the final charge on the cloth? We look at A. Electrons, when they move from the rod to the cloth, that would make the rod to be positive and the cloth to be negative. So A is not correct. We want a situation where electrons are in excess in the rod rather than the cloth. And B is giving us just that. So B, electrons are going to the rod and the rod becomes negatively charged. C and D, these two are just outright wrong. Number 25. A wire is a uniform circular cross-sectional area. Which statement is correct? A says the resistance of the wire is directly proportional to its cross-sectional area and inversely proportional to its diameter. In other words, A is saying when cross-sectional area increases, resistance will also increase. And we know that's not true. Wires that have a greater cross-sectional area, wires that are thick, they have less resistance than wires that are thin. So A is out. The resistance of the wire is directly proportional to its cross-sectional area. Okay, so this same point we just said it cannot be. Let's go to C. The resistance of the wire is directly proportional to its length and inversely proportional to its cross-sectional area. Let's check. Resistance is going up when the length of the wire is long. Well, that is true. A wire that is longer offers more opportunity for resistance than a wire that is shorter. So a wire that is longer has more resistance than a wire that is shorter. Let's look at the second option. Resistance is inversely proportional to the cross-sectional area. That is true. When cross-sectional area goes up, resistance goes down. And that is the meaning of inverse proportionality. They go in opposite directions. So our answer here will be C. The diagram shows the current voltage graph for a metal wire. What can be deduced from the graph? Okay, as voltage increases, the temperature of the wire increases. Well, we do not see that. As the voltage increases, the temperature of the wire decreases. Again, we do not see that. As the voltage increases, the resistance of the wire increases. Let's see. From the equation V is equal to IR, we can say R is equal to V over I. Now, if we look at this graph, gradient is I over V. So when the gradient is constant, it means R is also constant. Now, the question here is saying resistance of the wire increases. No, the gradient is constant here, so the resistance should be constant. We have our answer at D. A battery is connected to a circuit. It is switched on for 1 minute. During that time, there is a current of 0.4 amps in the circuit, and the battery supplies a total of 48 joules of energy. Which row gives the charge that passes and the EMF of the battery? Okay. We know that charge is equal to current multiplied by time. So the current, we are given 0.4, and the time we are given 60 seconds, 1 minute here. So the charge is going to be 0.4 times, we have 24 coulombs. Let's look at the EMF of the battery. We know that energy is equal to I multiplied by V multiplied by T. That is current times PD times time. Now, making V the subject of the formula, we have energy, which is 48, divided by current, which is 0.4, and time, which is 60 seconds. That gives us V as 2 volts. So our answer is going to be C. Number 28. The circuit diagram shows two identical lamps connected in parallel to a cell. 3 ammeters X, Y, and Z are also connected in the circuit as shown. Which statement about the current in X is correct? A says it is equal to the current in Y and to the current in Z. Let's see. The current that passes through X comes to this junction here. We call it a junction. And it is going to be split into current that is going to pass through Y and current that is going to pass through Z. So current in X is equal to the sum of current in Y and Z. A is not correct. B says it is less than either the current in Y or the current in Z. Considering the explanation from A, B is not correct as well. C says it is equal to the sum of the current in Y and the current in Z. Then that is true. We get to the junction, current is split, one goes to Y, the other goes to Z. Goes to Y, the other goes to Z. So C is our correct answer right there. A student connects the circuit shown. Which switches must be closed for the bell to ring without lighting the lamp? We want to close the circuit for the bell without closing the circuit for the lamp. So we have to close here and close there. Then there is a complete path for the bell, but it's broken here for the lamp. So we are looking at 2 and 3. We are looking at 1 and 3, sorry. 1 and 3. That is B. Number 13. The diagram shows an AC generator. The graph shows the potential difference between points X and Y plotted against time. A positive value of PD indicates that X is more positive than Y, which diagram shows the position of the coil at point P on the graph. If we look at point P, we notice that the PD is at its peak. All these points, these are peaks. And we can only have peak potential difference when our coil is in a horizontal position. This is because in the horizontal position, the coil will be cutting maximum flux or maximum field lines. So B and D are out. Now the task is to find between A and C, because these are the horizontal positions. And we get our hint from this statement. A positive value of PD indicates that X is more positive than Y. So the peaks which are here at the top, these peaks here, they happen when current is flowing in this direction from X to Y. So we are looking at this flow of current. Okay. Then, if we look at the diagram here, we see that our P is on the negative side. This is the positive at the top there, and this is the negative. Positive side, negative side. So, for P, it means Y is more positive than X. So, the flow of current is in this direction. Then we go to Y, then we go to X, and we continue. Now, this is a generator, and we can figure out the movement of current, the relationship between current, force, and the magnetic field by using the right-hand rule. So if we do the right-hand rule, we can see the force is going down. We see because we have an arrow pointing down. So force is going down on this side. And the field is going in this direction. That is north to south. So the field is going in that direction. So current must come this way. Current must come this way. So let us see the setup which is going to allow current to come in that way. We have current coming in this way. We have the north, we have the south, so the field will be in this way. And lastly, we have our thumb going downwards. Just like we have here, the thumb is going downwards, that is the force, and the field is going in that, and the current is going in this direction. So C here is the correct answer because it is lining up exactly with this diagram that we have here. So we pick C. Number 31. An electron moves into a uniform magnetic field. The arrow shows the initial direction of the motion of the electron. The direction of the magnetic field is into the plane of the page. In which direction does a force act on the electron when it enters the magnetic field? Okay, when an electron or a charged particle experiences a force inside a magnetic field, that is an example of the motor effect. So, with the motor effect, you use the left-hand rule. So, if I do my left-hand rule, the field is pointing into the page. The field is pointing into the page. And the current is pointing in this direction. An electron is negative. We know that negative charge and conventional current, they oppose in direction. So this is current, this is the field, and the force will be downwards. So the force here is going to be towards the bottom of the page. This is the thrust or force. Which statement about a transformer is correct? There is an alternating current in the core from the primary coil to the secondary coil. Well, the transformer moves energy from the primary to the secondary coil through induction. So there is no current which actually moves from the primary to the secondary directly through the wire. Current is going to, or energy is going to be transferred from primary to secondary through electromagnetic induction. So this is not correct. An alternating current in the iron core induces an alternating current in the secondary coil. Actually, the alternating current will be in the primary coil, and it induces alternating current in the secondary. Okay, C says, an alternating current in the primary induces a direct current in the secondary coil. The current that we induce will be alternating, not direct. Then lastly, an alternating current in the primary coil induces an alternating voltage across the secondary coil. This is correct, and it is an example of Faraday's law. How are positive and negative ions formed from atoms? A positive ion is an ion that has more protons than electrons. So if you have an atom and you remove an electron, you are going to leave an ion which has more protons than electrons. So add positive charge to the nucleus. Actually, we don't get positive by adding protons to the nucleus. That process is very difficult. So this is not the right way. Add positive charge to the nucleus, that's not correct. Remove electrons from, so C and D are the only remaining options here. The negative ions. During chemical reactions, we see electrons moving to some atoms. This makes the atom to have more electrons than protons. So add an electron to the atom. This is correct. So our answer is C. We don't remove positive charge from the nucleus. It's possible to do so, but it does not lead to formation of negative ions. You see movement of positive charge, movement of charges from the nucleus, you see that during radioactivity. And it does not lead to formation of these positive and negative ions. So technically, we pick C. A nucleus of element X is represented as 5626X, which is an isotope of element X. Isotopes have same proton number. Other things can be different, but the proton number must be the same. Because isotopes, they should be isotopes of the same element. So we look for a proton number of 26, and we find it on B. Number 35. A radioactive source is placed near a detector connected to a counter. 210 counts are recorded by the counter in 3 minutes. The background count rate is 20 counts per minute. What is the correct count rate for the radioactive source? Okay, when we record 210 counts, it means we received 60 counts from the background. So let's see how this becomes so. We divide 210 by 3, we have 70, 70, 70. So we were receiving 70 counts every minute. Now, of these 70, 20 were due to the background. That is the rocks, the cosmic rays, the lab material that might be releasing radiation, etc. So these 20 came from the background. These 20 from the background, these 20 from the background. Now, for every minute, it means 70 minus 20, the radioactive source was contributing 50. Here it was contributing 50 and 50. So for every minute, the radioactive source was producing 50 counts. And the extra 20 were coming from the background. Our answer for 35 is A. The background count rate measured by a radiation counter is 40 counts per minute. With the counter close to a radioactive source, the counter reading is 960 counts per minute. Okay, so the count rate of the source would be 920 CPM. This is the count rate of the source because 960 is source plus background. Okay. The half-life of the source is 20 minutes. So what is the reading of the counter 1 hour later? So after 20 minutes, we are going to have half of 920. So 920 divided by 2, we get 460. So that's 20 minutes. Then after some more 20 minutes, we get 460 divided by 2. The source will be giving us 230. And after some more 20 minutes, the source will be giving us 230 divided by 2, 115 counts per minute. So 20 minutes plus 20 minutes plus 20 minutes, this is the 1 hour. And the source is now producing 115. Now we take this 115 and we add the background count rate, because the background is going to remain at 40 counts per minute, so we assume. So 115 plus 40, we get 155. So for 36, our answer is C. Number 37. Which planet on our solar system is nearest to the sun, and what is the nature of the planet? Okay. For the planet that is nearest to the sun, it will be Mercury. So we are now looking at A and B as possible answers. C and D can never be true. Now, when we read about the accretion model, which is a model we use for the creation of the solar system, we learn that the particles that are nearest to the sun, they were competing with the sun to gather materials like the nebula, which was all over the place. But since the sun is much bigger, the sun is like 99.2 or 99.8% of the solar system. The sun is really huge. There's a stronger gravitational field. So the planets that are nearer to the sun, they were basically losing competition to gather the nebula, to gather the space dust with the sun. So the sun took all the space dust, or most of the space dust, it went to the sun. And these items, they remained as rocky planets. The sun is so hot that if any gas were to gather around these planets near the sun, those gases will receive so much heat and they will vaporize. They'll vaporize and they will leave this planet. That is the reason why you see the planets which are far away from the sun, where it is less cold, those are the planets which are giant gas planets. So Mercury must be rocky. There is a lot of heat near Mercury. This Mercury cannot keep its gases. Number 38. Number 38. A space station orbits the Earth at a distance of 7,000 kilometers from the Earth's center. It makes 15 orbits in every 24-hour period. What is the speed of the space station in its orbit? So, we know the orbital speed is equal to 2 pi r divided by period. Now, the r in this formula is orbital radius. That is the 7,000 kilometers given here. And t is the period of orbit. That is the time it takes this space station to complete one orbit, and that is 24 divided by 15. If we punch that in our calculators, we have 2 pi times 7,000 divided by 24 over 15. Okay, we are going to get 27,488, and this is the nearest value to that. So number 38, we have D. Which nuclear reaction powers a stable star? A, we have nuclear fission of hydrogen. We have nuclear fission of nuclei producing hydrogen. Well, in the stable stars, we don't have fission, but we have fusion. Fission is when a bigger unstable nuclei breaks into two smaller nuclei. In the stars like our sun, we actually see smaller nucleus coming together to form a bigger nucleus. Okay. Option B says nuclear fission. Again, they are saying fission. Wherever they are saying fission, that answer is wrong. C, nuclear fusion. Well, that's better now. Nuclear fusion of a krypton nucleus and barium nucleus. Well, this is not the elements. These are not the elements. Then D, nuclear fusion of hydrogen nuclei producing helium. That is the correct one. We have hydrogen and hydrogen forming helium. Which stages in the life cycle of a star are listed in the order that they occur? Option D is the correct option here. Thank you guys for watching. Continue to subscribe. Bye-bye.